I will be covering the machine learning segment of our data science module. So before we get into this, it is recommended that you all study the previous notes where the data cleaning, data wrangling, and everything is discussed. So I will not be doing that part here onwards. I'll be focusing on the slide sets that are on machine learning, supervised learning, unsupervised learning, classification, and clustering. So um, before we get into the technical stuff of ML, we should know some basic things about data. So, ML is basically us using data to train a model. And before we train the model, we have to figure out how the ML models use the data, how they see the data. So, first of all, we have our data set. Let's assume we're doing some sort of study about um, humans, where we are going to gather information, data from a large number of people. So, when it comes to practical scenarios where ML is used, it's not just a data set of 100 data points, it could go up to thousands and 10,000s of data points. So, ML deals with big data sets, very large data sets. So now that we are assuming that we're going to do some sort of study about humans, we have collected our data set, and each individual data item is called a data point or a sample. And then we have separate variables. Now about humans, we'll be collecting maybe age, gender, height, weight, and skin color. So things like this, variables. So these variables are called features or attributes in the context of ML. And also, there are two main types of features. Now um, we're gonna now that we have collected our data, we are gonna let's assume that it's in a CSV file with the columns for the variables and each data point as a row. And we're gonna define our target variable depending on our requirements. Let's say our requirement is to find out whether a person is a female or a male based on other information like age, skin tone, height, and weight. So then, in our case, since we are going to focus on finding out whether the person is a male or a female, the gender is going to be our target variable. That is the output variable that an ML problem aims to find. Then the other independent variables apart from the target variable are called input features. So these are the variables or the features that is fed into the model to learn. So based on these features only, the model learns to predict the target variable. Now, the target variable is always depending on our problem, on the scenario that we are going to work on. However, this target variable can be two types. It could be a categorical variable or a continuous variable. So in the example that I just took, it's a categorical variable because the variable falls under a specific class or a category, male or female. Now, if we take height, for example, now let's say we are going to predict the height of a person. In that case, our output variable is going to be a numerical value that can fall anywhere within a range. So then this becomes a continuous variable. So based on the nature of our output variable, whether it's categorical or continuous, the models that we will be using is different. So different types of variables require different types of models. Then we have two main subsets of the data. So now that we have gathered a huge amount of data, now that we have a big data set, we are not going to feed the entire data set in the model for training. So what we do is we are going to split the data set into two parts as the training set and the testing set. So what happens in the training set is this portion is fed into the model for the learning. So data and information are taken from this training set is what the model learns on. And then we have the testing set. This testing set is a portion of the same data set that we are going to use to evaluate the model, to check how the accuracy of the model is, to see how well the predictions happen. So like that, to evaluate the model, we are going to use the testing set. So basically, the standard train test split is 80 to 20, 80% for the training set and 20% for the testing set. But depending on our scenario and depending on the model performance, this may vary. But usually when we are fitting a model, we start with the 80-20 split, and then we try out different splits if we want to adjust the model. And also this training testing, how are we going to split this? Now we have a random huge data set, and how do we decide what type of split that we have to do? So this actually is a different segment where there are many types of splitting techniques. So the most common splitting technique is the random split. So a random split is when we just randomly pick data points into the training set and the testing set. And there's also many other techniques where splitting is done. And sometimes in some cases there's also a thing called the validation set. That is not a mandatory set. Um, that is required only if our model is actually it's an optional set depending on our case that we are working on. So the main two subsets are the training set and the testing set. And next we have labeled data and unlabeled data. So what type of model we will be using, what type of ML techniques that we are going to use also depends on whether we are working with labeled data or unlabeled data. So what is labeled data? Labeled data is when the categories or the classes for each data point is given. For example, like I said before, now that we have collected data of humans and we are going to work on gender as our output variable, if we have specifically mentioned the males and females, the males are labeled as males, females are labeled as females. If the label is given, then um, it is label data. So if this feature is not taken, now if we have collected every other information except for the gender, like if we have not labeled this, then this becomes unlabeled data. So the predefined categories are not there. So depending on whether we are working with labeled data or unlabeled data, we will be choosing the ML techniques. So now that we've learned about the data usage in ML, we'll see what actually a machine learning model does. What a model does is it learns the patterns of a data set. So now what we have done is we have split our data set into training and testing. So we take the training set and then we feed this into the model, where the model studies this data set and learns its patterns. Now, if I continue the same example, we are feeding the information about the height, weight, skin color, age of the people to the model, and then the model trains on that, and then it predicts whether it's male or a female, makes inferences about new data similar to training data. So if we feed in the same features of a random person who is not in our data set, the prediction of our model will be will be the gender. So if we want to, this model is trained to predict the gender. So in that case, we are going to take a random data point and then we are going to input that into the model, and then the model will give us the prediction. So this is what an ML model does. Trains itself using data and then makes inferences about new data that are similar to the training data that have been fed. Now, if we train the model on human data and if we input data of a cat into this model, it is not going to give us a proper prediction, because always the model is specifically making inferences similar to what it was trained on, not a totally different domain. So if we want information about cat and dogs, we'll have to train our model based on their information. So ML is mainly three parts. We have supervised learning, we have unsupervised learning, and we have reinforcement learning. And based on supervised learning, we have classification and regression. In unsupervised learning, we have clustering, dimensionality reduction, and rule mining. So here we'll be covering classification mainly, and a little bit of regression, just the theoretical aspect of it, and clustering also. Uh, yes, reinforcement learning will not be looked into as it's not in our course content. Okay, so before we get into um, detailed ML techniques, let's take a look at the flow of an ML problem. So what happens first is we have to define the problem we are trying to solve. In the previous case I took, the problem we are trying to solve is to find out whether a person is a female or a male. So to solve this problem, we have to figure out what type of data that we are going to collect. So after defining the problem, what type of data we have to collect, what features are required, how many data points are we going to work on, all of this is decided, and then the data collection happens. It could be either using a survey or interviews, or many different kind of methods are used, and the data is collected and um, brought into one place for proceeding with the rest. Then, since we have maybe collected data from different sources, from different collection techniques, and the people who have collected the data, the inspectors, they may have different ways of formatting. They may have collected data in different ways. So once all of this data is brought into one place, we have to clean the data. So we have to bring it into one standard method where the ML model can easily understand. So for this, we have to clean the data. We have to deal with the missing values or outliers, if any, and all the cleaning things. And then we have to do feature engineering. What in feature engineering is, sometimes what we have collected, the features may need some alterations. Like if we need more features, we can use a feature we have and then we can expand it. Likewise, there are many feature engineering techniques. So we have to do feature engineering also if it's required um, on the data set. So after we do all these steps, the data wrangling part, we will get a proper standard data set that is ready to be used with our model. So after this, we are going to perform the train test split. Here, we are going to split our data set into two parts, as the training set and the testing set. And then we have to choose what model that we are going to use. So depending on the type of our problem, whether it's a classification problem, whether it's a regression problem, whether it's an unsupervised learning problem or a supervised learning problem, we have to choose what model we can use. So in actual cases, we don't just select one model, we usually go for a few models and then evaluate all the models and pick the best model for the practical usage. But that is why model selection is important. Sometimes um, we may have selected a model that when there are better models for this specific problem. So model selection is very important. We have to understand what type of problem we are dealing with, and we also have to figure out what is the best model out of all the available models as well. And then using the training set, we are going to train the model, and after that we will be testing the model. And after the testing is done, we are going to evaluate the model using evaluation metrics like the RMSE, the MAE, or the precision or recall accuracy. Likewise, for different types of models, we have different types of evaluation metrics. So we are going to evaluate the model and then we are going to tune the model. So after we evaluate the model, we figure out whether we have reached the level of accuracy that we want to uh, achieve. So if this is not achieved, we are going to the tuning phase where hyperparameters of the model is tuned um, for better um, performance of the model. So each model has different hyperparameters. It could be the loss function or the number of epochs, like that. So many technical words. Um, so model has so many hyperparameters. So this tuning is required. So the default parameters rarely works. They don't just We can't just take the data and put into a model and it's not going to work. So we have to uh, tune this. So after that we are going to retrain the model. And sometimes if it feels like the testing, like if it feels like the split is biased, we may have to go back to the test split and split the data again and come back to the training segment. So likewise, this may happen so many times until we reach a desired level of accuracy, a good amount of accuracy without no overfitting or underfitting. Because just because your model is 100% showing 100% accuracy does not mean it is a perfect model. So it may be overfitting, so it may be underfitting. So we have some diagrams that we drew to understand whether it's overfitting or underfitting. Likewise, a lot of evaluation should be done before we decide that the model is performing well. So after good performing and after perfect tuning, we will be deploying the model. There's a small issue here. This should come over here into evaluating. So after evaluating only, we are going to deploy, not during the tuning phase. Yes, so we're going to deploy the model, and then afterwards it will be continuously maintained throughout. So also when the new types of data comes in, we will be retraining again, doing the retraining phase. So likewise, that is also a part of maintenance. Okay, so now we will move on to supervised learning. So what is supervised learning? Um, Now, previously we discussed that we have labeled data and unlabeled data. So when we have labeled data, we will be the models that are trained using labeled data falls under supervised learning, because we have a guidance, because we have what the possible outputs. So this is supervised. And each data point has a known output. Now, if I take the same example, all of my data points are either male or female. So all of them have a known output. So here we can apply supervised learning for this example. Supervised learning falls on the two parts, classification and regression. So first we'll look into what classification is. Okay, so classification is done when our target variable is a categorical variable. Now, the requirements for classification is, first it should be labeled data, then it should be categorical data. The output variable should be categorical. So output variable is labeled and categorical. We can go for a classification. So the objective of classification is to predict which specific class an input belongs to based on its features. So this will be the type of example that I've been talking about all this time. Based on the input features such as height, weight, age, and skin type, we will be predicting whether the person is a male or a female. So this is classification. But it's not just general classification, because when it comes to classification, we have multiple types of classification. We have binary classification, we have multi-class classification, we have multi-label classification, and then we have imbalanced classification. So first we'll look at what binary classification is. So in a binary classification problem, we have only two distinct classes. Two distinct classes means there are no overlaps. So one data point cannot fall into two classes. One data point only has one class, male or female. And then that might not be the best example these days, but we'll go for other things like email filtering, spam or not spam, and then in an exam result, pass or fail. Once there can't be a student who is pass and fail at the same time. So likewise, it has to be two distinct classes, binary, hence two classes only, and then one label per data point. Here we are going to distinguish between two opposite situations, 1 or 0 situations. Then we have multi-class classification. Here also we are going to work with distinct classes, but in our problem we have multiple classes. Now if we take the examples I've taken here, shape identification. So in our data set we have circles, squares and triangles, and hence we have more than two classes. Because of that, it goes into a multi-class classification. A shape cannot be a circle and square at the same time. Because of that, these are three distinct classes, no overlaps. These kind of situations calls for multi-class classifications. And in a multi-class classification, this is going to the prediction will be the most accurate single category. It will always the output will always be a single category. Then we have multi-label classification. Now here's where the tricky part is. Sometimes you may confuse multi-class and multi-label classification. So what happens in multi-class classification is always distinct classes. There are no overlaps. But in multi-label classification, there are overlaps. One data point can fall into multiple classes. Now if we take an example, we have some sort of picture, a picture of a beach, for example. Now we have labels: water, sun, nature, forest, um, green. Now these are our five classes. We have water, sun, nature, green, and forest. Now if we take a picture of a beach, beach has water, beach has sun, and it's a picture of nature. This picture falls under all three labels. So because of this, this particular input falls into multiple classes. If we use a multi-label classification model, all of these categories will be identified. The the classes or the labels in this data set is not mutually exclusive. They are not distinct. We have overlapping classes. So the difference between multi-class and multi-label is, in multi-label classification, there are overlapping classes, and a multi-label model will always identify all the relevant categories that a data point falls under. And then we have imbalanced classification. So in imbalanced classification, we are going to detect the minority class. So in a binary classification, we are going to go with the majority, the one that suits the particular um, the data point. But here we are going to look at the minority class. We're going to put more weight on the minority class. For example, in fraud detection or like a rare disease diagnosis. Now, if we take thousands calls, it's only like what, five or like 2 to 5 calls are only fraud. So we are going to look at the minority where fraud occurs using an imbalanced classification likewise. So it's usually two distinct classes. It could also be multiple, but mostly focused on two distinct classes. Okay, so now we'll take a look at some classification algorithms used in ML. So first we have decision trees. This could be either binary or a multi-class classification. And then we have SVM. This is specifically a good binary classification model. And then random forest. This is a good multi-class classification model. And we have neural networks, which can be either binary or multi-class. And we have naive Bayes, which is a good binary or a multi-class classification. And we have k-nearest neighbors, KNN, which is more focused on being a good multi-class classification. And then we have logistic regression, which is a binary classification. Here's the tricky point here. A logistic regression may have the word regression, but it is a classification model. This is something to keep in mind. Okay, so now we will be going into in a few individual classification models. We'll be looking at how the math in. Okay, so the first classification algorithm we are going to look at is called the k-nearest neighbors, KNN for short. This is a supervised learning algorithm and it's best for multi-class classification. So here KNN actually works on three strategies, I would say. The first one is distance-based learning. So the algorithm analyzes the distance between the data points. So the algorithm works on calculating distance between each data point and a categorization next. So that is looking at a k number of labeled samples physically closest to the new point. So now that we are working with distances, let's assume that we have a new data point that we want to make a prediction on, and this data point is somewhere in the middle of our existing data points. So what we do is we calculate the distance between all of these data points, and then let's say we list it down in ascending order. But then how do we know what data points to mainly look at? Like how many data points to look at? So that is K. We have to define K to look at, to decide how many data points physically closest that we are looking at. And then we have majority voting. So now that we are looking at a K number of data points, we are going to use majority voting to vote on the most common label found among the neighbors. So the most common label is hence assigned to the new data point. So now that we've been talking about K, and before we get into an example, we look at how to find the best K um, for our algorithm in the specific case. So now, in this case, K plays a very crucial role in the accuracy of a model. So if K is too small, this could create noise, and if K is too large, it would be biased, which both causes the model accuracy to drop. So theoretically, K can only last between 1 and n. N is the total number of data points in our data set, in our in our training set, actually, in our data set. So why? Because the closest number is 1, because we cannot go below 1. We'll at least have to compare with one data point. And then n, because that's the maximum number of data points we have. So theoretically, k should fall under this range, and it always will. So we have three main techniques that we're going to talk about in deciding the best K. The first one is cross validation. So what happens in cross validation is, this is more like a practice test for the algorithm. So to find the best K in KNN, this is more like a trial and error type of method, where first our training data is split into folds, like 5 or 10 equal folds. After that, um, the model is testing different k values, starting from k equals 1 up to, like, so on. It keeps on testing different k values on these folds, uh, different groups of our data set. So after that, we are going to calculate the accuracy scores for each k value. And after that, the highest accuracy score that is taken, like the k value that achieves the highest accuracy score, is taken as the best k. So this cross validation technique is quite a computationally intense technique. So we don't really manually do the calculation. This is we'll be using this is like a separate algorithm. Cross validation is a separate algorithm. We actually code it and use, and it's too intense to do manually. And we have the elbow method. So in elbow method, um, the accuracy and the k value for the multiple and the point where it diminishes is taken as the k value. So how do we find k using elbow method? Is that we're going to run the KNN algorithm multiple times, starting from k equals 1, and then for each k, we are going to record the error rate. So this is usually taken by cross validation, and then we're going to plot this in a graph against the k value. So then we're going to find the elbow in the graph. So we're going to find the point where the error rate drops significantly, and then when the graph starts to flatten, so this is more like an L-shaped graph, and we're going to find the elbow point with the lowest error rate, where the error rate drops, and this particular k value is taken as the best k using the elbow method. So this too is quite a computationally intense technique, where we cannot really manually calculate. So the next technique is what we can use in manual calculation, that is the square root of n rule. So when capital N is the total number of data points, the best k is taken by the square root of the total number of data points. So let's assume our data set has 16 data points. Our k value that we are going to consider would be root of 16, that is 4. Okay, so now that we know different ways to find the best k, how are we going to calculate the distance between 2 points? So let's take x as the new point and y as the as any existing point. The most common method to find the distance between 2 points is using Euclidean distance. Euclidean distance. So Euclidean distance measures the straight line distance between 2 points, and this is done in a multi-dimensional space. This could be either continuous or numerical data. So once the data is plotted in a graph, you can use the formula and find the Euclidean distance. And the next is the Manhattan distance. So this technique is used when the data points are following a grid-like path. So mostly when we are working with vector data, high dimensional data like vectors. And then we have the Hamming distance. So this is used on categorical variables only. So this is usually when we compare strings or sets of data rather than focusing on the physical locations. So if the new point is the same as the existing point, the distance becomes 0, and if they are different, the distance is recorded as 1. So this is how these are like three different distance techniques. So depending on the type of data and our objective of the classification, we can use the preferred method of finding the distance. And now, what are the steps? So how do we classify using k nearest neighbor classification? So first we have to select a k number using the previous techniques discussed. So here I've taken a random example with 25 data points and three classes: a square, triangle, and a circle. And I've defined the k value using the square root method to be 5. And next we are going to calculate the distance between the new point and every other point in the training set. So this is our new point, and we will have to calculate the distance using a preferred method, let's say Euclidean distance. The distance between this new point and each and every data point, all of these, each data point we have to calculate the distance and list them down. And then we are going to determine the k number of nearest neighbors. So what we do is, after calculating the distance between all of these data points, we will list it down most probably in the ascending order. So after listing down in the ascending order, we are going to take the closest data points. So now, since in this case k is 5, we are going to choose the 5 closest neighbors. So now, since there's like a 25 data points, I have not done the distance calculating part, so I've skipped directly to the third step, where I've chosen 5 neighbors closest. I'm assuming those are the closest, so 5 neighbors. And then we are going to count the neighbors, labels of the neighbors. So now, considering the chosen neighbors here, you can see we have one square, one triangle, and three circles. So here we are going to use the majority voting next, that technique, and we are going to assign the category label with the maximum count to our new data point. So in this case, that's a circle. So the class of the new data point would be a circle. Right. So this is how we do k-nearest neighbor classification. So now we'll be looking into naive Bayes, the next classification algorithm. This too is a supervised learning algorithm where our output is focused on a categorical variable. This is a probabilistic algorithm where probability techniques are used, and this is best for multi-class and binary classification. So here there are three techniques that we look into. First is the probabilistic classifier. So here the class is predicted by calculating the probability of a new data point belonging to each category, and then the naive feature. So here the naive feature means that the algorithm assumes that every feature is independent of every other feature. So we assume that the variables are independent variables, and the output is a predicted label. So that is the category with the highest calculated probability. So before we move into the steps of the algorithm, let's look at the mathematical foundation, more like the statistical foundation, which is the Bayes theorem. So we've learned the Bayes theorem in statistics. So here we'll be using the Bayes theorem to calculate the posterior probability of a data point belonging to a specific class, given that it has the if it has some features. So this probability is read out as a probability of a data point belonging to a specific class C1, given that it has the features F1 and F2. Um, right. So to calculate this, we require the Bayes theorem. We have the probability of occurring a feature given the class, and then the probability of the data point belonging to a class. This is multiplied and by the probability of a feature occurring. So here I have given out the descriptions of each of this. So this might be a little bit confusing, theoretical part of it. When we go into the example, it will be much clearer. So now let's look into the steps. The first one is where we are going to calculate the prior probabilities. That is the probability of a specific class occurring. So first we're going to take the count of data points in that particular class, and then we're going to divide it by the total number of samples to get the probability of some data point belonging to a class. And then we have to find the likelihood probabilities, that is the number of we're going to consider the features, and then the count of features in this particular class, and then total number of divided by the total number of samples belonging to the particular class we are looking at. And then we are going to calculate the posterior probability by using Bayes theorem. And finally, we're going to compare the probability values of each class and then classify accordingly. So now this is a very detailed example that we are going to look at. We will be taking a basic example of classifying emails into spam or non-spam. So here we are going to take 10 emails, the total of 10 emails, where 4 are spam and 6 are not spam. So this is our training data set. 10 emails, 4 spam, the label is given as spam, and not spam is labeled as ham. So it's just a label, it doesn't have meaning, but the label definition is not spam. So 6 of them are not spam. And inside the 10 emails, we have considering the word offer. So this is a feature in our data set. If we put it in a tabular format, one column would be spam or not spam, which is the state. The other column would take this feature containing the word offer, which will be a yes or no feature. So some emails contain the word offer and some emails don't. So out of the spam emails, 3 of them have the word offer, and one of the non-spam emails also have the word offer. So now we're going to look at the first step, calculating the prior probabilities. So the baseline chance of an email being spam or ham before we read it. So the probability of a email being spam is 4 out of 10 because we have 4 spam emails, total of 10. And the probability of an email being not spam, 6 out of 10, 0.6. And we are also going to calculate this, the probability of the feature occurring, that is the probability of having word offer, the total number of emails with the word offer. So we have 4 emails that has this word offer. We have 4 emails, so therefore we have the probability of 0.4. Then we are moving to the step 2, finding the likelihood probability. So this is we are finding the probability of having the word offer given that this email is spam. So we have found out that this email is a spam email, and then how many of that has the word offer. So we found that there are three spam emails who has the word offer. So here it goes as 3. Total number of spam emails is 4, and the probability is 0.75. So similarly, we are going to find the likelihood probability of the other occurrence, not spam, um, given that the word offer is there. Having the word offer given that the email is not spam email. So here we have one email from the not spam section having the word offer, and then we have 6 non-spam emails. So there the probability is approximately 0.17. And we're moving to the third step, where we're going to apply the Bayes theorem to find the posterior probability. So now a new email comes and it has the word offer. Is this a spam email or not? That is what we are going to calculate by finding the posterior probability. So now here, now given that the word offer is included, the probability that the email is a spam is taken by the Bayes theorem formula here. So so here we get, after calculating, 0.75 probability. And then we also have to consider the other probability, the other class, right? So not just one class. The other class is not spam. So now we're going to calculate the probability of the email being not spam given that it has the word offer. So after the calculation, we get that it's 0.25, approximately 0.25. So now now that we have our simplification, we are going to now that we have our calculations, we are going to compare the two values and then classify this email accordingly. So now 0.75 probability of this email being a spam, and 0.25 probability of this being a not spam. So the algorithm classifies this email to be a spam email. So this is a simple binary classification example. We can always do more examples and figure out. This is just to understand the flow. Okay, so after naive Bayes, we have logistic regression. So like I said before, logistic regression is not a regression algorithm. It is a classification algorithm. Here, we're going to predict the probability that an input is belonging to a specific class. So for this, we are going to use the sigmoid function. In logistic regression, the sigmoid function is used. So in this, we can, in this sigmoid function, what it does is it maps a real valued number. So this real valued number could be from any range. And the sigmoid function, what it does is it maps this number into a value between 0 and 1. So let's assume our values range from 1,000 to 100,000. So that's going to be a really big range. So to handle this data in a much convenient manner, we are going to use a sigmoid function to map these real valued numbers into the range between 0 and 1 for calculation, for ease of calculation. So first, what we are going to do is we are going to calculate Z based on the input features. So now input features, like we discussed before, the notation is X. So we are going to take the weighted sum of input features. So each of these input features is given a weight for the logistic regression problem. And we are going to calculate the weighted sum of all of these input features, which will be Z. So this Z is can range from minus infinity to plus infinity. It could be any value. So we are going to calculate the Z value, and then we are going to pass it through the sigmoid function to get a value between 0 and 1. So if our value that we get out of the sigmoid function is more biased towards 0.5 if it's greater than 0.5, and it's like more biased towards 1. The class is defined as 1, like uh, the class we define as 1. And then if our sigmoid value is less than 0.5, more biased towards 0, the class is given as 0. So we're going to, first of all, we have to define what our class 1 and class 0 is. Since this is a binary classifier, we have two classes. So if we take our previous example, it could be a spam email or not spam case. So if we are looking at spam, it could be class 1, and not spam could be class 0. Likewise, we have to define the classes according to the question we are looking at. And then according to the sigmoid value we are getting through the sigmoid function, we have to predict the final class based on that and then classify accordingly. So that is how logistic regression works. And with that, we will be concluding the in-depth discussion of classification algorithms. So now that we have predicted our values, now that we have classified our new data points into a class, and we have given them a specific class, using our classification algorithm, we discussed a few models. How do we know if our model is good or not? So we have to now evaluate our model, right? So let's assume our model classifies whether the emails are spam or not, but it has classified a actually spam email as a non-spam email. So likewise, the models make mistakes. It's not always 100% accurate. So we have to evaluate our classification model to understand how good this model is. So if our model is not good, we have to retrain. Um, we have to do some amendments. We have to tune the model and retrain. So to figure out whether we have to do it, to figure out what type of tuning we have to do, we have to evaluate our models. So to evaluate classification models, we have a few metrics. The first one is the confusion metrics. This is like the most basic technique. So after fitting a classification model, we always draw out the confusion metrics. So here we are looking at four different cases: the true positive case, the false positive case, the false negative case, and the true negative case. So here we have four possibilities: two success possibilities and two unsuccessful possibilities. Now we're looking at the actual value and the predicted value. So this is where the test data set comes in. We're using the test data set to evaluate the model by comparing the actual class a data point belongs to and the predicted class of it. A true positive case is a success, that is the actual value is also positive and the predicted value is also positive. So let's take an example of a medical diagnosis. So this example here that I've drawn a confusion matrix is for a medical diagnosis where we are testing if patients have some sort of disease. So we've taken a sample of 10 patients and we are going to test if they have a particular disease or not. So now after the classification, after running through the classification model, true positive means we have diagnosed two patients correctly. So that is we have diagnosed that two patients have this particular disease and actually also they have the disease. Then we have the next case, the false positive. So this is a false alarm. So what happens is actually uh, the actual data point is the class is negative, but the predicted is positive. So mapping back to the example, um, our model predicts that this one patient has the disease. It comes as a positive outcome, but actually this person does not have the disease. So this is a false positive, a false alarm. So the next one is false negative. So this is a miss situation. So we have predicted that this person does not have the disease, but actually he has the disease. So this is a type 1 error. Uh, the statistical term for this is type 1 error, and the statistical term for false positive is type 2 error. And The next case is a true negative. So this is where we diagnose correctly again. Actually also it's a negative, and predicted is also negative. So actually the patients they don't have the disease, and our model also predicts that they don't have the disease. So after the confusion matrix, we are moving on to accuracy, precision, recall, and the F1 score. So for all this, we are going to need our true positive, true negative, false positive, false negative counts. So the first one is accuracy. So the accuracy, we're looking at the proportion of total predictions that were correct. So the correct predictions are the true positive ones and the true negative ones. We are going to add this and divide by the total number of predictions. And then the precision. The precision is the quality of the positive predictions. Now, totally positive predictions, we have totally true positive ones and false positive ones. What the precision looks at is the quality of the positive predictions. How well can our model predict positive outcomes? So here we are going to take the true positive as the numerator, and the addition of true positive and false positive as the denominator. And next we are looking at the recall. Recall is the true positive rate. So considering um, the model, how capable of how capable the model is to find all the positive cases. So here we are going to take the true positive and false negative cases as the denominator, because false negative means actually also this person has the disease, but it was recorded as negative. So predicted as negative. So here we are going to take the actual positive cases, and from that how much were identified. So true positive as the numerator, and the addition of true positive and false negative as the denominator. And the next matrix is the F1 score. So here we are going to combine the precision and recall into one metric, because this is actually very useful when the classes are imbalanced. So this is the formula here shows how to calculate the F1 score. And after this, we have the ROC curve, the receiver operating characteristic curve, and the area under the curve. So we are going to plot the true positive rate against the false positive rate. The true positive rate is the recall. The false positive rate, the formula for the false positive rate is given here. That is, we are going to measure the proportion of negative cases that were wrongly classified. So we are going to take the false positive rate into consideration, and we are going to map these. We are going to plot these in uh, a Cartesian plane and get a plot. So in this plot, we are going to get a curve, and higher this curve, the better the model. So and then we are going to look at the area under this curve. So area between the x-axis and the curve, the area under the curve. So if the area under the curve is 1, this is the perfect model, which is actually not the case in most of the cases. Then the model, if it's 0.5, it's a guessing, it's at a guessing state. So it's more like 50-50 chance of being accurate or not. And if the area under the curve is less than 50, it's definitely giving wrong answers consistently. So for it to be a good model, it has to be the area under the curve is um, it should be between 0.5 and 1. So when plotting the ROC curve, we are going to use the y-axis for the true positive rate and then the x-axis for the false positive rate. Now we're going to look at regression. So previously we discussed classification, that is under supervised learning, and now regression, the second type of problems under supervised learning. So previously for classification, we looked at categorical variables. So here we are going to predict a continuous variable. Our output variable is a continuous variable. So we are going to predict a continuous variable based on one or more predictive variables in regression. So for evaluation of regression, there are a few evaluation metrics where mean squared error and the R squared are two of the prominent ones. So the goal of regression is to find a mathematical mapping from the input features to the numerical target. So basically forecasting sales or predicting house prices based on other different features falls under regression. So we have linear regression, which is a ML model, and then we have a decision tree regression, which is used for regression, and then we have SVR, support vector, which we can use for regression. And yes, so there's not many in-depth insight into these regression models. It's just a simple overview. We have next to talk about decision trees. Decision trees is actually a very interesting ML algorithm because this actually can be used for both classification and regression. So decision trees can be used when our target variable is categorical and when our target variable is continuous. This is a graphical representation. A decision tree uses a graphical tree-based structure to do the classification or the regression. And so the core idea of decision trees is to break our big data set into smaller homogeneous subsets using a recursive process. So this is a recursive process where we have to do it a few times, and we're going to break our data set into smaller subsets. We have to keep a few terms related to decision trees in mind. We have the root node, that is, if we consider the entire population or the entire sample before any sort of splitting, the very first node, this is called the root node. So as you can see, the graphical representation here I have given, the topmost node is noted as the root node. And then splitting is a process, so it's not exactly drawn on the graph here. Splitting is where we divide a single node into a few subnodes, and it's the process of dividing. And then a decision node is a subnode that splits into further more. So these dark green boxes are decision nodes because they can be broken down into more nodes. And then a leaf node is a terminal node. So that means the node cannot be split into further. All of these light green ones, it doesn't have more child. There are no more children, no child nodes. So these are leaf nodes. And then we have a branch or a subtree. So if we take a smaller subsection of the fuller tree from the big tree, we are going to take a small subsection starting from a decision node, and this can be named as a subtree or as a branch from our decision tree. So now let's take a look at how we are going to use the decision tree, the steps. In this case, we are only going to look at a classification example using decision tree, but we do use it for regression as well. But mathematically, it's much feasible to simply look at a classification problem. So when we look at the steps, first we have to select the best attribute. This is so now in our data set we have so many features, so many input features. So we have to first figure out which feature splits the data set better. Now these are the decision nodes. These attributes, they are the decision nodes. So we have to find out what's the best split. We're starting with that. And then we are going to create a decision node. The best attribute is assigned as a decision node. And then we are going to split the data set into smaller subset based on the values of the attribute. So now if we consider a binary example, yes or no, a binary feature would be yes or no. Like um, so in based on that the values of the feature, we are going to split the data set into smaller subset, and then we are going to continue this recursively until either of these stopping criteria is met. So we are going to repeat the process and keep on adding decision nodes into our tree until the one of these stopping criteria is met. So the first stopping criteria is all the data points in the node belong to the same class. So if we have all of the finally after doing this multiple times, the remaining data points, if they all belong into the same class, we can stop. And then when there are no remaining attributes to split on, so after we have considered all the attributes into the splitting, then we can stop. And then when there are no more data instances left, so if we have considered all the data points, then also we can stop. Okay, so now after this we have now built the decision tree using the previously discussed steps. We have built our tree. So after we built the tree, we are going to start at the root node. So the root node is where the entire data set is. So we are going to start there, and then we have to test cases for each node. For each attribute, we are going to test cases. So each of the nodes are test cases being evaluated. And then we are going to follow down the branch corresponding to the answer of the test case. We're going to test multiple test cases, and we are going to go down the branches uh, corresponding to the respective test case, and then until we reach a terminal node, until we reach a leaf node, we are going to continue this down, and that final answer would be our classification or our regression value. So this might be a bit confusing when I just talk about the steps, so we'll dig into an example and try to figure this out. But before we go into an example, you might have the question, how are we going to select the best attribute? Like first in the step 1, here I've told that we have to select the best attribute, the best feature. So techniques for that, we have to select the best attribute. So for that we are going to use attribute selection measures. We have two main attribute selection measures used in decision trees. The first one is entropy and information gain. The second one is Gini impurity, the Gini score. So first we'll look at entropy and information gain. Entropy measures the randomness of a data set, like how uncertain values of a data set are. So that is what entropy measures, and it is either a 0 or a 1. the maximum value entropy can have is 1, and the minimum value entropy can have is 0. It's always between 0 and 1. So if our output is 100% certain, if it's like if there's no impurity, if there's no randomness in the data, the entropy value would be 0. So if it's a maximum uncertain, so if it's like if reaches the maximum level of uncertainty, there's so much randomness, then our entropy would be 1. So there are of course fluctuations in between. So our entropy value would always fall between 0 and 1. And after calculating the entropy, using the entropy value, we are going to calculate the information gain. So this is where we are going to see how well a specific attribute separates the training. So using the information gain only, we are going to um, find which feature has the best information gain. So the feature with the highest information gain is considered as the starting attribute. So how are we going to calculate the information gain? So the information gain is the entropy before we split minus the average entropy after the split. So this will be much clearer when we get into the example. So here we have an example calculated using entropy and information gain method. In the example, we have taken a sample of 8 students and we have two attributes. The first one is whether they studied or not. Here we have a binary attribute, yes or no, and another attribute, attended class. So if they attended lectures, attended class, yes or no, another binary attribute. So this is like a very simple example. And then we have the result. So the result is whether they are pass or fail, if they pass the class or if they fail the class. So first of all, what we have to do is we have to find out the probabilities of the classes. The first is probability of passing. So that would be we have equal number of people passing and failing. 4 out of 8 for passing and 4 out of 8 for failing. And then we are going to calculate the entropy, the total entropy of the entire sample. So here we're going to apply the formula and then we get 1.0. So maximum uncertainty there because so we have see exactly 50-50, yeah. So since it's exactly 50-50, it is very hard to find. Now we can't just guess our um outcome. So therefore we encounter maximum uncertainty in this case. So now that we have calculated the entropy, we are going to calculate the information gain. So now for information gain, we have to calculate information gain considering each attribute because we are going to select what the best attribute is. So first we have the first attribute we are going to take is studied, whether they studied or not. So we have two outcomes, yeah. For studied, we have two outcomes. The first one is yes, and the second one is no. So now we have to count the number of passes and fails for each of this. When the information, when studied equals yes, 3 people have passed and 1 person has failed. So now we have to calculate the entropy for studied equals yes. So in that case, we're going to consider the pass section and the fail section, and we get an entropy of approximately 0.81. And then we are going to calculate information gain, sorry, entropy of studied equals no, where 1 person has failed and, sorry, 1 person has passed and 3 people have failed. And we are going to calculate the entropy likewise. Here also we get an approximation of 0.81. So now we have to find the average entropy after the split. So if we are considering study as our feature, we have to consider that and then calculate the average entropy. So this is how we calculate the average entropy. Here we have the probability of passing times the entropy, and then probability of failing times the entropy. So we get the average entropy. So now we are going to go for the information gain. So before split entropy, the maximum uncertainty 1.0 minus 0.81. So here we are getting an information gain of 0.19. So you can see. So if we consider studied as the main as an attribute, the information gain would be 0.19. So similarly, we are going to calculate for attending classes as well. So after calculating the information gain for attended class, you can see that we have gotten an information gain of 1. So comparing the two attributes, we have studied and attended class. We can see that attended class takes the highest information gain, has the highest information gain. So in this case, we are going to start with attended class. We are going to select attended class as the root node. Then we are going to draw the tree where attended class yes equals pass and then no equals fail. Likewise, we are going to split this. And because these are pure subsets, the reason is what is a pure subset? So now when we consider attended class, all of the data points are covered. So here, considering the stopping criteria, we have no more data instances left. And all the data points in a node belong to the same class. Now, all of the data nodes in this example falls under attended class. So we can stop the splitting. Therefore, we are stopping the splitting under this, and our this will be our final tree, a very simple tree. So if any data point comes with attended class yes, we are saying that the student have passed, and if not, it goes as fail. So this is like the simplest example out there. So when we are going as a recursive recursive method, when we are doing this over and over, this will be replaced with the leaf nodes will be replaced with more attributes, more features, and it will go beyond. So in this data set, if a student attended class, they passed, and if not, they are failed. So this is the calculation using entropy and information gain. And next we have the Gini impurity, the other technique of figuring out the attribute, the splitting attribute. Okay, so Gini impurity measures how often a randomly chosen element from the set would be labeled wrong. So here we are going to measure how wrong our classification could be. So using that, we are going to find the Gini value, and considering the Gini value, we are going to reduce the impurity. Now we are going to measure the impurity first, and then we want to reduce the impurity. And then we are going to select the attribute with the maximum impurity reduction as the root split. So this is the formula for Gini impurities. We can use either formula. Gini score will always be between 0 and 1 again. So again, I'm going to use the same example for this. First, we have to calculate the initial Gini value, which will be 0.5 in this case. So after substituting here the probability values, and then similarly we are going to calculate the Gini value for each instance. Studied equals yes, studied equals no, and then the weighted average of the Gini. And after that, we're going to do the impurity reduction considering the attribute studied. And similarly, we are going to calculate the impurity reduction given considering the attribute attended class. And as you can see, the impurity reduction of studied is 0.125, whereas that of attended class is 0.5. So the maximum impurity reduction is at attended class. So we're going to take that as the root. So it gives the same outcome as using entropy and information gain in this case, but in some cases it could change but not very different. It could be very similar, but there could be small changes. Okay, and now we are moving on to unsupervised learning. Before moving on to unsupervised learning, quick summary about what we did before. We discussed the basics of machine learning, and we looked into supervised learning models, and classification algorithms, and the theory of regression, and also decision trees as which can be used as a classification algorithm and a regression algorithm. So after all the supervised learning, we'll be moving on to unsupervised learning. Okay, so supervised learning works with labeled data, whereas unsupervised learning works with unlabeled and unstructured data. So the goal in unsupervised learning is to find the structures or the groupings in data. And since only the input features are provided with no labels, it's the algorithm's task to find the structure or the grouping of the data. So we have three types of key algorithms in unsupervised learning: clustering, association rule learning, and dimensionality reduction. Um, we have clustering is grouping similar data points into clusters. So techniques like k-means clustering or hierarchical clustering is used here. And then we have association rule learning. So this identifies interesting rules between variables in that data set. So uh, how the data sets, they have specific rules in them. When it comes to variables, there are rules and constraints. So these are considered in association rule learning. And then we have dimensionality reduction. So this reduces the dimensions. So converting a high dimensional data set into something small like 3D or 2D. So techniques like principal component analysis or T-distributed stochastic. Likewise, there are multiple dimensionality reduction algorithms as well. And here, there's no effort to label. So actually, labeling data takes a lot of time and effort. Actually, it's a total different job role out there. And also, because there are no labels and because there are no constraints like this, labeling constraints, unsupervised learning may reveal unexpected patterns or segments in the data. However, it's pretty hard to measure the accuracy because we have no proper guidelines. And results may be subjective, and sometimes interpretations might require domain knowledge to interpret because we don't have proper labels for the outcomes that we are getting. Okay, so now we are coming into clustering, an unsupervised learning technique. So this is where we group similar data point into categories without prior knowledge of class labels. So here we do not know the class labels, but we're still trying to group similar data points into categories and define categories later. Um, a few real world applications of clustering would be customer segmentation, retail business, in security, biological science, image processing, etc., etc. So clustering, we have multiple clustering techniques. The first one would be centroid based clustering. So in centroid based clustering, we're using the arithmetic mean, which is the center of a data set, to form groups. So K means clustering, K medioid clustering, fuzzy C means clustering. So likewise, there are so many centroid based clustering techniques, and we will be talking about K means clustering. So K means clustering is one of the most popular centroid based algorithms. Do not confuse K-means clustering with K-nearest neighbor classification. Do not mix up the both. This is K-means clustering here is an unsupervised learning method, and KNN, the K-nearest neighbor classification, is supervised learning classification. Okay, so back to K-means clustering. So this is a very popular centroid-based algorithm, and this splits datasets into non-overlapping subgroups. So the subgroups, the categories here are not overlapping. So here we have to find the optimal K again. So here we use two methods. We have the WCSS, within cluster sum of squares technique, or the elbow method. So similar to the previously discussed elbow method. Here we are going to use so WCSS is a metric that we use to evaluate how compact the clusters are, so how clustered they are together. So lower values are preferred because we are going to group into clusters, we are going to break him into clusters. So when the compactness is less, it's easier to cluster. And using WCSS, we are going to plot the graph to find the K using the elbow method. Okay, so um, the steps is, first we are going to initialize the data points and initialize a few k data points as centroids initially, and then we are going to compute the Euclidean distance between each point and the k centroids, and then we are going to assign each point to the nearest k. So we're going to assign a few k points as initial centroids, and after that we are going to compute the Euclidean distance between each point and these k, and we are going to assign the closest points to the k, and then we are going to recompute the centroid for each cluster. Now in the first step we are going to form some clusters roughly, and afterwards we are going to update the centroid for each cluster by calculating the mean of the points, and then we are going to keep on continue computing the Euclidean distance, and then finding the nearest clusters, and then computing the centroid again, likewise repeating step 2 and 3 until uh, there's no big change in centroids. So when the difference between the centroids becomes significantly lower, we are going to stop the iterations, and then the final cluster uh, are then created. So here we are following an example. It might be slightly unclear. Yes. So here is a small example. First, we are so the question is that we are looking at 6 different cities, and each city has two numbers, its area and its population. So we want to automatically group similar cities together. So we are going to pick a random k. So we are deciding that we want two groups. So we're going to decide that we want two clusters. So k is equal to 2. We are going to take k equals 2. And then we're moving to the next step. So out of the 6 cities, we're deciding that we want two groups, and here we are taking 2 points randomly as the centroids. We have taken two random points. And now in the second step, we are going to um, cluster them accordingly. So we are going to calculate the Euclidean distance between each of this and the distances accordingly. And now after that, we have created random clusters. So just keep in mind that the random centroids that we have placed are just made up center points. We drop them anywhere during the chart when we are going through the iterations, and then we are going to assign every city to its nearest centroid. For each city, we measure which centroid is the closest, and we have assigned. So afterwards, we are going to move the centroid into the new average. So after that, we have calculated the new average points here, new centroid, two new centroids. And after that, we are going to reassign every city into the new pin positions. So now that we have calculated two new centroids, we are going to calculate the distance again, and we are going to reassign and update the centroid. So here there isn't any change so far because the distances are showing likewise. And then afterwards, we are going to move the centroids again. We're going to repeat the calculation of uh, centroids and reassigning the points again. And we are going to stop when nothing changes. So, like twice it didn't change, and then again in the next step also it didn't change. So, we are going to stick to the same point because there's no change in the assignment. And yes, so that's basically how we're going to do our cluster. So this will be our cluster 1 and this will be our cluster 2. And now there might be the question, how did we just randomly select our K? Like how do we, now we selected K to be 2, and how did we select it randomly? So here is where the WCSS is calculated. You can see the formula here. We have calculated the WCSS. Each time we measured it, basically how spread out the cities are inside their clusters, uh, and we plotted it. We plotted it in this case against each case. Say the 6 cities, K equals 1 to 6. We have calculated WCSS, and we have then plotted it in the elbow curve. And then as you can see here, this is where the significant drop is from the highest to the point, which creates an elbow. So we've taken that as the right choice for K. So that's about it for K-means clustering. And then now we have hierarchical clustering. Yes, so in hierarchical clustering, what happens is either we merge small groups together or we split a single large group into multiple subsets. The first one is the agglomerative clustering. So that is a bottom-up approach where we start with distinct clusters, n distinct clusters, and every data point has a cluster, and we are going to group them by similarity, the closest ones together. We are going to merge them into one cluster based on the distance, and we are going to repeat this until we merge all the points into one single cluster. And the next technique is decisive clustering. This is a top-down approach. So this is the focus of this is to split. So this is done based on dissimilarity, unlike points in different clusters. So when you visualize hierarchical clustering, where it's more like the bottom of a tree. The branches show that the clusters were merged. It's more like a tree-like structure, a dendrogram. Right. And then in hierarchical clustering, we talk about cluster linkage. So this determines how clusters are merged or split by measuring the dissimilarity between them, like how dissimilar two clusters are, how different two clusters are. Here we are going to measure that. So usually the distance metric used is Euclidean distance. So there are many linkage techniques. The first one is single linkage. So here the shortest distance between two points in any two clusters is computed, and the two closest clusters are merged together. And this is very sensitive to outliers. And the second one is complete linkage, the max linkage. Here we are going to consider the maximum distance between clusters, and we are going to merge the two clusters with the smallest maximum distance. So when we list down the maximum distances in order, the one with the two smallest distances are merged. And then we have average linkage. So here we are going to calculate the distance between all pairs of 2 points in clusters, and then we are going to take the average distance in each. And the two clusters with the smallest average distance is then merged. Then we have the Ward's linkage. This is merging the clusters with the minimum increase within a cluster variance. This considers the variance, um, this method. Okay. And after centroid based clustering and hierarchical based clustering, we also have density based clustering, which groups points based on high density areas are separated into low density zones. So density is considered. And then the next one is distribution based clustering, which assumes that data belongs to clusters based on statistical probability. So that where probability is considered in creating clusters. So with that, we are going to finish the ML segment of the data science module.